So now it's 12, you can start.
Okay, thank you. Good afternoon, everyone. My name is Wang. I'm from Wageningen University. Today, the topic of my presentation is comparison of UAV and airborne-based sun-induced chlorophyll fluorescence over different crop canopies. This is a joint work between Wageningen University and the ULH Photo Center, and it is supported by SenseEco. As we all know now, in 21st century, there is a very rapid increase in food demand. So how to solve this problem is a challenge. And photosynthesis is a major factor that limits the food production. So have a bad understanding of the crop with the photosynthesis. It can help us to increase crop yield and estimate the crop production. Fluorescence is a byproduct of photosynthesis. When a leaf absorbs sunlight, there are three pathways for the absorbed energy. The middle one is the photosynthesis, and the other two are heat emission and the fluorescence emission. So the fundamental connection between fluorescence and photosynthesis makes fluorescence a direct and a good indicator of vegetation photosynthetic activities. Sun-induced chlorophyll fluorescence is fluorescence signals that produced in natural daylight, and this signal can be acquired by remote sensing techniques. SIF signals are included in the reflected radiance, but SIF signal is very weak. It's only accounting for 1 to 5% of the reflected radiance. Currently, there are different remote sensing platforms to measure crop SIF. The first one is ground-based, like a tripod-based or tower-based. These platforms can provide SIF for long-term at a very high temporal resolution. However, it lacks flexibility to measure SIF within the field. Satellite-based platforms can give us a SIF product at regional and global scale, but the spatial resolution is too coarse to get very accurate SIF information over the small-scale farmland. Now we have airborne systems such as HyPlant. These systems has high performance and can provide safe information at an intermediate scale between ground-based and satellite-based levels. But these systems can be very costly, and it's very difficult to get safe measurements at a very high temporal resolution. So it's not so suitable for agriculture application, for example, the crop growth monitoring or the stress detection. Luckily, now we have UAV. UAV are the platform, flexible platforms and very cost effective. These platforms can provide data at high temporal and spatial resolution. So UAV-based SIF has great potential in agriculture, like precision agriculture. A research question is, can the UAV-based systems measure reliable, safe, like high performance airborne systems. This is still unknown. By answering this question, we can have more insights on the following two questions. The first one, are UAV-based systems able to bridge the spatial gap in SIF between ground and airborne levels? And can they support the calibration and validation of airborne SIF products? So to answer this question, we compare SIF acquired by UAV and airborne systems over different crop canopies. There is the spatial distributions, there are no development, and linear relations are compared. In our work, HyPlant and UAV-based FluorSpec systems were used to acquire data. HyPlant is an image spectrometer and it has two modules. In our study, it only fluorescence module was used. This module covers 670 to 780 nanometers. For UAV-based FluorSpec, it has a non-image QE Pro spectrometer. This spectrometer has the spectral window of 630 to 800 nanometers. It has two channels. The upper one collects the irradiance, and the downward one collects the reflected radiance. And a RGB camera is also fixed with the QE Pro sensor here. So this is a picture when the HyPlant and the FluorSpec flew over the field at the same time. So the field campaign was carried out over an agricultural research station in Germany in a very clear weather condition. At that time, 7 crop types were growing in this field. HyPlant, airborne HyPlant systems and UAV-based FluorSpec systems flew over the field following a diurnal pattern for 4 times on this day. HyPlant flew at a height of 350 meters and results in a spatial resolution of 1 times 0.5 meters. FluorSpec flew at the height of 20 meters with a speed of 2 meters per second. So the size of the footprint is 8.8 meters. At the on the same day, we also collect some RAI and chlorophyll content measurements. This table shows the flex time of FluorSpec and HyPlant flights. So to retrieve SIF, we applied spectrophytic method to get HyPlant SIF, and spectral shape assumption from line discrimination SSA FLD to retrieve FluorSpec SIF. Both methods relies on the theory that decoupling reflectance and fluorescence is at atmospheric absorption bands. For example, the oxygen A and oxygen B band. For spectrophytic method, it applies the proper mathematical functions to describe the apparent reflectance and fluorescence at oxygen A bands, and the spectral window of 750 to 780 nanometers is used. For SSA-FLD to retrieve FluorSpec SIF, we have two assumptions. The first one is that we already know the chlorophyll fluorescence spectral shape, and the reflectance factor change linearly over the spectral window of 750 to 780 nanometers. So we can say for SSA-FLD to be a special case of spectrofitting method. This slide is about the improved geolocation of FluorSpec footprint. Before any comparison can be made, it's very critical to precisely locate the FluorSpec footprint and the georeference HyPlant maps, because we use the SIF of HyPlant pixels following FluorSpec footprint were averaged to compare with FluorSpec SIF. So for HyPlant data, it was already georeferenced before HyPlant SIF map were generated, and these maps have a high geometric accuracy. The positioning error was 1 to 2 meters. So now the major task is to accurately geolocate FluorSpec footprint. For we assume the footprint shape is a circle, and its size is a circle of the diameter at 8.8 meters. Then the initial central location of the footprint was given by the FluorSpec gene as information, but these locations needed to be improved for two reasons. The first one is that what we are interested in are signal source within FluorSpec footprint. The second one is that we want more accurate HyPlant SIF within FluorSpec footprint. So to improve the geolocation of the footprint, we use the FluorSpec RGB images and precisely georeferenced photon for RTK image. As we see from this figure, the distance between the RGB camera lens and the radiance optics is very short, only 13 centimeters. So we can assume that the center of the footprint was same to the center of the corresponding RGB image, and then we geo-rectified the FluorSpec RGB photos manually with the already well georeferenced RGB ortho mosaic. Afterwards, we assigned the central coordinates of the FluorSpec RGB photo to the concurrent footprint center of FluorSpec measurement. So this slide is about the results of the improved geolocation of FluorSpec footprint. From this table, we can see after the improved geolocation, flat 1, flat 2, and flat 4, The linear correlations between the FluorSpec SIF and the HyPlant SIF was improved, especially for flat 1 and flat 4. The R squares increased by 0.11 and 0.2. But for the third flat, the R squares remained same, 0.71. So this is because of the distance between the original footprint centers and the improved footprint centers. For example, for the flat 3, the average distance before, between the center of the footprint before and after the geolocation, it was 1.56. So if we look at this figure, we can see before the footprint before and after the geolocation were almost overlapped. Sorry, I forgot to say that the black circle were footprint locations and the footprint size before the improved geolocation, and the yellow circles are footprint after the improved geolocation. Even after the footprint the improved geolocation, the footprint between the repeat UAV flights still slightly spatial misaligned. For example, we can see for the first flight path of all flights, they did not overlap very perfectly. From this figure, we can say that for all for both the systems, HyPlant SIF and the FluorSpec SIF were well linear related for all flights. Especially for second flights, the R squares was up to 0.776. For the last 3 flights, we found the very similar regression coefficient, very similar intercepts, and the slopes quite close to 1. If we combine these 3 slides together and made the linear regression, we can see the linear relationship is still very good. R squares is very high. So this result shows the stable and the good performance of FluorSpec to measure SIF at the field level. But we also found the R squares was different for different flights. For example, for the first flight, it was 0.65, and the second one is 0.76. So we think that there were 2 possible reasons. For the first one, it would be the geometric accuracy. HyPlant SIF maps have high geometric accuracy, but it still has a 2 to 1 to 2 meters positioning error. And for the FluorSpec, the geolocation was improved, but it could be further improved considering the mold factors. So this could result in the difference and the variations in the SIF signals for the HyPlant and the FluorSpec SIF. The second reason could be the sun target sensor geometry, because we collect the data in the following diurnal pattern. So the different solar linear angle would affect the sun target sensor geometry. Also, due to the footprint and the mismatch, which we have already explained in this slide, it would lead to the difference in the footprint geometry and also vegetation coverages. For example, the canopy structure within different sampled areas would also have an influence on the sun target sensor geometry. This will affect the directional SIF observations observed by the sensor. This too.
Now, Wang, sorry to interrupt, but it's 20 minutes, so you have maybe 5 minutes. Can you finish in 5 minutes?
Yeah,
perfect.
Yeah, I can do it. Yes,
thank you.
The render. So this is these two figures shows the spatial patterns of FluorSpec and HyPlant SIF. The left one is the diurnal and the spatial patterns of a HyPlant SIF, and the black circles indicate the FluorSpec footprint positions. And the red figure, it is the patterns of FluorSpec SIF. The gray color map, it is the HyPlant SIF values, but in a gray color scale. So we can see the similar and clear patterns for both systems. Different crop types had different SIF values. For example, for winter wheat 1 here, and then the spring barley 2 at this area, they have a relative higher SIF values due to the close green canopy. In maize field, this area, the SIF was lowest because the vegetation coverage was low at that time. We can also find spatial variations within the same field. For example, in winter wheat 1 at this field, for the third flat, the SIF values can change from 0.7 to 1.4. Besides the spatial pattern, we can also see a clear diurnal pattern following from flat 1 to flat 4. So this is a figure shows winter wheat 1 field. This is a maize field. For the diurnal dynamics of both systems SIF, we can see for the same crop, there is the diurnal trend is similar. And for most crops, there was a diurnal pattern lag path, but not for every crop. So, for example, for the winter wheat 1, winter wheat 2, and the spring barley 1. This pattern is not for every crop, but it makes sense. There are two reasons. The first one is a flat path mismatch, and the second one is angular effect, which we have already explained in the previous slides. For the flat path mismatch, it would result in variations in footprint geometry and coverage within the same flat path for different flats. For example, for spring value 2, the footprint covers more greenness, and the angular effect can be caused by the changes in the syntactic viewing geometry in a continuous mapping mode, and caused by the changes in solar zenith angle. So to conclude, FluorSpec SIF is highly correlated to plant SIF, and we found pronounced diurnal patterns for both systems SIF. Similar and clear spatial variation of SIF over different crops for both systems were found. HyPlant SIF proves the ability of UAV-based FluorSpec to measure SIF. That's all. Thank you. And your comments on the questions are very welcome.